I'm Rania.
I'm Duran.
Oh, man. So today we're going to talk about something very interesting. So if you haven't already, you guys can actually go look at the Ryan Duran podcast show, GitHub, and we actually have the super vulnerable job application out now, a new version of it actually, which we're going to discuss. What is it then? Like we're going to discuss about the AES CBC, weak cipher mode, stuff like that, right?
AES ECB, the electronic code book cipher mode. Super vulnerable job application, as you all know, we have a number of different endpoints already. Our newest endpoint is this super secret endpoint, and that points to the class Cipher Action. Cipher Action is what's responsible for, effectively, it acts like a proxy of sorts for the actual application. You can send it an action where the data pertaining to the action is encrypted, and then it goes off and it executes the action. In this way, you're going to see that it has a lot of similarities to the insecure reflection, which we already have, the reflective action. And if you haven't seen that video, I definitely suggest you take a peek and see what you think and see what you like. So when we look at this, we're going to note that the Cipher Action takes in a new VO called Secret Squirrel VO. It's going to kick back results just like the reflective action. When we look at the actual index call, it calls to this BLO gateway, again, just like what you saw in reflective action almost immediately. The VO itself is actually pretty simple. So when we look at the VO, we expect to get an action name. Now, we'll look as to what the BLO is doing, but you'll note while this has insecure reflection or unsafe reflection, it's a little more tightly bound than what we saw in the reflective action. So it does accept an action name. It also accepts parameters. Now, those parameters are key value pairs. In this case, the key is the setter that you'll call, and then the value is what you pass to the setter. Meaning, since this is effectively a proxy for a given action, if we wanted to do something like the file action or the project's action, we would pass in project's action, and then we would pass in the different setters that we need to set if we're setting something. For example, project ID or ID, and then you would give it the actual ID tied to that. The other thing that takes in is the RESTful method. The RESTful method, those are just your HTTP verbs, get, post, put, delete, things of that nature. Inside of all of this, like I said, we wind up calling the BLO gateway. The BLO gateway, as we can see here, does what all the gateways do. Remember, we follow a gated architecture. These gates are there to provide that basic level of protection, but they also make it much easier to perform code reviews. When we have good, safe coding guidelines, it's very easy to say, okay, you have this public variable that is inappropriately exposed. You have this variable that is not final and it needs to be final. You have this class that's inappropriately exposed. And it also provides an actual API, a traditional API methodology to programming by hiding all the internals, all the juicy stuff, be they package private or other methods. So inside of super secret BLO, we see this secretly call action. This is what we wind up calling from the BLO gateway. This method, it takes in that action name from the secret squirrel VO, and then it decrypts it. That's that first step that we see here. It has to go through and decrypt what that action name is, because the key here is we are effectively providing a secure tunnel for all of your traffic. In case you're maybe in a hostile environment, say you're in a public wireless, say it's a mobile phone application or what have you. So we decrypt that action name, and then we load the action right here. And you'll notice that we're binding that namespace. So we are still vulnerable to unsafe reflection, like what we saw before, but what you'll see is you're tied to everything inside of this package, and here's the kicker, the sub packages. That means that you could hypothetically make a call to these interceptors or to the pre-result listeners if you wanted to. I point that out because it's absolutely vital to recognize that even though this binds you a little bit, it doesn't make that reflection safe, especially if you have actions inside of here that shouldn't be called to. For example, we could make a call to unknown action. We could make a call to authentication action again, but you've already authenticated, but you could. So just recognize that you can leverage this to call these inner classes, any of the classes inside of packages. You could also do it to call actual inner classes, so a class inside of a class, if you so desired. So we still have that unsafe reflection. It's not as bad as if it were completely unbound, meaning you could call any class, any method, but it is still there. The next thing you see us do is we create a new instance. So first we load that action, then we create a new instance of it. And after we've created a new instance of it, we march through those parameters and we're calling the setters. Here again, you see us decrypt. So we're decrypting both the key and the value. And of course, the setters, we know what those look like. If we were to go to projects action, for example, right here, what we're talking about when we talk about the setters is, of course, anything that's set. So set project ID, set project, set project, set CSV export, set basic CSV export, things of that nature. That's what this code is doing here. That's what those parameters are. And remember, that key is the second half of the setter. So it would be the CSV export. It would be project ID. It's the variable name because we're tacking set on. One thing you should notice is how we march through the methods. So we grab all of the methods and then we march through your parameters and we march through the methods. Anyone who remembers their big O notation knows this is inefficient. But the point here wasn't for efficiency. In fact, maybe the point was partially inefficiency. This is mimicking something that you see in a lot of the deserializers today. After we've done that, you'll see we set that request method. Remember, the request method, like I said, is really just get, post, put, delete. And it, again, decrypts that. And once it's decrypted it and set it, then we execute the given action. So the order really quickly is, of course, we decrypt the action name, we load the class, we create a new instance, we call to the setters based on the parameter, the data inside parameter, which we decrypt both the key and the value for each one. And then we decrypt the RESTful method, after which we can actually call to execute the action. And so you'll note here, you can call any action inside of that, but you can also call any method that's a setter method. And that's one of the keys here, is this isn't being bound to something where you have annotation or anything like that. The methods are only being bound by the name, the set whatever name methodology. So this unsafe reflection in multiple ways, it's not the most unsafe, but it definitely could be problematic because you still can call things that you shouldn't be able to call. And the key here, though, is going to be the encryption. So before I go anywhere, really quickly, I'm going to go into this network traffic encryptor decryptor code. So we see this here. This is our oracle. This is the application's decryption and encryption oracle. It's called a Cipher oracle, or just an oracle. And we see the two halves here. Something really important that you have to understand is that we're using AES ECB, AES, of course, Advanced Encryption Standard, ECB being Electronic Code Book, PKCS7 padding. What this tells you is we are working with padded ciphers. One thing you'll note really quickly is when we were looking at the BLO, it's going to return the results of the action's execution, but it also returns error messages. And in both cases, those then get bubbled up as part of result, which go to the end user. I would point out here too, we serialize the object and encrypt it. So now recognizing that and recognizing that we're doing padding, you should see that you potentially have the opportunity to do a padding oracle, or if you're older, a padded oracle attack. You'll also hopefully recognize that we're using ECB, and ECB, which is the default for Android and things of that nature, because it's efficient. I can run the electronic code book in parallel, and we'll see why here in a minute, but it's also very low memory and CPU intensive. And that is because the way it operates, if I have a string of A's, for a given key, it will always produce the same string for every segment. So for every block size. So if I have a block size of 16, for example, or 15, it will produce the same string, same ciphertext for each one. So let's actually look at this. We're going to log in real quickly. And we see here, we recognize that the action name is going to be encrypted, that the parameters are going to be encrypted, that the data is going to be encrypted. And let's say that we've decided we want to mimic projects. We know that if we're doing projects, when we look at the struts.xml, projects, of course, points to project action. So we're going to make a call to project's action. Now, what I've already done is I've created a magical oracle. And this magical oracle, all it is, it's really what's called a sled. So the sled calls to the oracle. I don't need to know how to encrypt or decrypt what you have. I just need to know to call to the oracle. So we're going to type in project's action. It's going to encrypt that text. So we grab this and we're going to pump it into action name. Now the RESTful method, we could try seeing what happens when you don't put anything in, when you don't set it. We could maybe try to play with it in a couple of different ways, but we do know RESTful action, or the RESTful method, allows get. So what we're making right now is going to be a standard call to project's action, and it should list out something similar to what we have in this call, where I see my project and I have the data. So let's actually make this call. Let's see what we see. All right, so we got some ciphertext back. So what we're going to do is we're actually going to look at this. We'll use the sled to call to the magical oracle again. And the magical oracle tells us, here's the data. You'll notice this actually matches what we had in our standard call to projects. Let's do a couple of things, because you probably don't know how to build your sled or build your oracle. Let's actually take a peek at how this code is working. So if you were doing something like a code review, and that means that you actually get access to this, or maybe you figured out that they were doing AES ECB, and there's an easy way to figure that out, and I'll show you in a minute. But we'll look at it from a code perspective first. Let's start at the top of this. We already know the entryway for encrypt and decrypt. And let's take a quick peek at what all they have. So they, of course, have this private static final string called hex. It's just A through F. we have a string 1 with the value of act of, we have string 2 with the value of the, a string 3 with a value of being bad, right? We see there's this hex to byte. That one we're just going to ignore. It's pretty self-explanatory. 2 hex, that's pretty self-explanatory. We already saw encrypt and decrypt. And by the way, if you don't know, BC is Bounty Castle. Okay, so we see this method get encryption key. And we notice here it's public static and it returns an array, right? And this is actual code from an actual system out there. This actual code that's unfortunately common in a lot of mobile products.
I also wanted to ask you how common do you see AES what is ECB? Yeah,
it's the default for Android.
Okay, so a lot of Android uses this too.
A lot of iPhone and the Apple tablets.
iPad.
What are they? Yeah. Thank you. Sorry, I don't have any. I absolutely hate Macintosh.
He hates Apple.
But iPads and iPhone applications also tend to have the same vulnerability because most of the time they're communicating with the same server infrastructure. So if you're building an Android application and you're just using the default, well, you're going to mirror that. You're going to mirror that in your Apple products. And that's a problem because if you are using something like a phone or some mobile device and you're on public wireless, you'll inappropriately think that your data is encrypted when in fact it is not encrypted in a meaningful manner. And again, we'll get to why. Since we have this public static get encryption key, what we're going to do is we're actually going to cheat because let's say when we look at this, we can see they're taking string 2, 1, and 3 and combining them together. So this is a hard-coded key. So they have hard-coded AES key. You should definitely hit them on this. And it doesn't matter that they've split it up into 3, right? And the reason why it doesn't matter is because it's still present in memory as 1. But here's a fun one. Let's actually use this reflection vulnerability and let's call to network traffic encryptor and we'll call get encryption key and let's see what we see. So when we called this, it came back with base 64 encoded string, and we see that base 64 encoded string is in fact the act of being bad, which is our key. So this worked. This worked beautifully, meaning I can take the fact that they're using a hard-coded key and now I can pull that data out. But it wouldn't matter if the key is hard-coded, right? So long as I have this method, I can pull it. Here's the beauty about a hard-coded key, though. Number one, I know every single client is going to use this same key. So if this is an application that's used en masse, then everyone's using the same key. We also know that once we have the key, now I can decrypt everyone's traffic. Anyone who's using this application, we can decrypt all of their traffic. We also know we can now create our own tool that will encrypt and decrypt. That's the beauty of this. But let's say you didn't have this exposed method. If it's a mobile application, you can download the APK or IPA or what have you, and then you can decompile that, and you might find the key. The keys were all hard-coded, so when we grabbed the mobile application and decompiled it, we got the keys. And that meant that, number one, we could do so much more, but number two, it's so much easier to encrypt and decrypt data. But I'll tell you, we didn't even need that because we'd already broken it beforehand. And we'd broken it for a couple of different reasons that are inherent with the algorithm. All right, so let's look at our sled. And we're going to do a quick test just to show you what I was talking about earlier with AES ECB. And it's with any electronic code book mode. It doesn't matter what algorithm you're using, it's the actual mode itself. So we see 7A0. When we look, we see 7A0. And we can find 7A0. And again, 7A0. 7A0. 7A0 over and over and over again. That's electronic codebook, because what it does is every single time you have this string, it's going to encrypt it the exact same way. So we look at this, and here I have 15 characters. This 15 character string with this particular key will always produce this, no matter if it's the first block, the second block, or the 100th block. So when we take this long string of A's, like this, we notice that we can see this repeating block over and over and over again. So we know for a fact, anytime we see 7A0635, so on and so forth, that's a block of A's with this particular key. Because the way AES ECB, the way, in fact, all electronic codebook implementations work, regardless of the algorithm, this is just a problem with the mode, block A will equal block B will equal block C if they have the same key and the same plain text. Doesn't matter if it's the 100th block or the first block or the millionth block, it will produce the same one each time. That way you can, in parallel, encrypt each one. Also, I don't need to keep in memory what the value of the prior one was. That's why you see the electronic codebook used so heavily in mobile applications. It's parallelizable, so it's faster, but it's also more memory efficient because I don't need to keep track of where I was before or even keep track of where I am now. But it means that it's vulnerable to frequency analysis. So I can either attack the key or I can attack the actual ciphertext. Either case results in the same exact thing. And let's take the easy, obvious issue right here, and that is the RESTful method. Well, in this case, RESTful method is bound to only a few different possibilities, the most common of which would be GET. The second most common would be POST. So what I can do is I can create a dictionary, and I have two options here. I can create a dictionary if I know the key of all values or all potential values. Alternatively, I can do the opposite. Let's say that we have a black box and I don't know the key and there's no way to get the key, not directly anyway. I can actually indirectly get the key if instead I go through and I map out all instances of the encrypted word get for different keys. I can actually monitor your traffic, and I can specifically figure out what key you're using by using, instead of a plain text to ciphertext dictionary, I use a ciphertext to key dictionary. So I'm working the other side of the equation. And this is actually a very simple thing to do. And we actually went through and we created a dictionary, which is, so for this particular one, I did frequency analysis and broke it via frequency analysis. I did a dictionary, and I did both dictionaries actually. I did manage to obtain the key, so I built out a dictionary of all possible values, but I also built out a dictionary given a single value because in my case, it was using XML. And here's the beautiful part. We know what the XML code is going to look like. In this particular case, it always had the typical XML header. But let's say it weren't XML and instead it were something like JSON. We know what the start typically is going to be. And if I have a good idea, because maybe I have a sample application, and I know for a fact that during this step, we usually see this kind of text, I can do that frequency analysis and break your key through the frequency analysis. So there are a couple of different real nice ways to do this. And it's really all up to you, the attacker. We can sit there and do frequency analysis by analyzing these different blocks. We can create a dictionary. And if you make a dictionary, it's gorgeous because I only need a dictionary for a single block because it's always going to be the same across blocks. So I think one of the biggest exercises for the reader is actually to go through and see if you can create your own oracle. See if you can, for example, understanding that they're using AES ECB, and even if they weren't using ECB, here's the beautiful part here. If they were using AES GCM, AES CBC, AES counter CTR, or any of the others, or if they were using Ghost or what have you, this vulnerability is going to be a key for you.
I'm Raniel.
I'm Duran.
And if you haven't already, please like, comment, and subscribe if you want more videos like this one. Definitely go check out the previous videos and then come back to this one if you haven't looked into reflection and all the other different things that we talk about in previous episodes or demonstrations. So this way that you can come here and kind of already have an understanding of it. But if you like this episode, please let us know, comment, email us, whatever you like. Until the next time.
Have fun. So let's take a peek where we're doing an attack. In this particular case, let's take a look at what happens if we do bit twiddling at the end of this string, because it is a padded string and we know it's padded. We're going to change the E to an F, and we see we get this pad block corrupted. The pad block corrupted tells us that this is actually vulnerable to a padding attack. And I can actually derive the ciphertext from a padding attack. And we can just automate this and away we go. I will point out that you can't use the same padding attack methodology for ECB that you would for something like CBC. So where you're chaining, you would have to make your own, because I don't know of one off the top of my head that's at least common and publicly available that attacks ECB, but it's actually very easy to do. Yes, the failure to properly handle errors is absolutely critical. There's so many vulnerabilities that come out of the error handling. It's not funny. You, of course, have the padding oracle attacks, but like you said, it can help you when you're doing something like SQL injection, regular expression injection. It can help you when you're doing local or remote file include. All kinds of vulnerabilities are really helped out by errors. And I think a lot of people underestimate the damage and impact that even very simple errors can cause. But that's the nice thing in this particular case, is we can do a padding attack against this implementation because they do pump that data out. And we can do a lot more as well.
So just to think, if they're doing that, would they go back and review the code and then formulate their own oracle, or it's something you just have to understand?
Yeah, I think it's important to recognize that the oracle in this particular case is something that you can ask and it will give you an answer, but you don't know how it works. You don't need to know how it works. You just need to know the answer. One of the nice things about it is you can create that sled that queries the oracle, and you can think of it as like a test bed where it queries the oracle, and that's where your chosen plain text and things of that nature, those vulnerabilities, that's how you're actually exploiting them. Is we query the oracle, we see what we get back, and then we query the oracle, we see what we get back. The nice thing about this, what a lot of people don't understand, is when you talk about the padding attacks are querying the oracle and trying to see what you get back. And because we know how padding works, the padding is actually very formulaic and it's well documented. It makes it very easy to do oracle-based attacks against them. And this is in addition to the whole frequency analysis and all of that kind of stuff. But I find it important for people to recognize the different attacks and the different methodologies that you can use for breaking the ciphers and for breaking the keys, because it can be so simple and it's not as hard as maybe it seems. You could review the code and create your own oracle, but you don't have to. One of the easiest ways is, in this case, to steal the code and just drag and drop it and make an oracle from there. But even better than that is to make a sled. So just make something that will query that server or query that code. If it's something that you can run locally, say it is a mobile application or it's a desktop application, I can query that code. I just need to know how to call it, and I can use reflection or what have you and call it on behalf while the application's running of the client.
So can we talk more about Sled? Like that's the first time I had heard that. Kind of think about it, I'm like, Santa Claus's sled is sliding.
Yeah, that's actually pretty fair.
But when you talk about sleds, I kind of want to make sure I truly understand and what's the difference between it.
So the sled is the tool you use that calls to the oracle. You can think of the sled as it's an application that either calls to the method or it calls to the action endpoint, whatever it happens to be. And all it does is it queries the oracle. So it's a vessel to get the data that you want. And it's really akin to a test bed. Yeah, so you definitely, I use the sled to make the dictionary, to make both dictionaries, rather than go through and create malicious. You can create a malicious oracle, and malicious oracles are fantastic. Or you can use the oracle that they have, or you could, if you have access to the code, obviously, just copy the code out and make your own oracle. If the keys are hard-coded, that makes it even better. If the keys aren't hard-coded, that's fine too. Because if the keys aren't hard-coded, now I can use that oracle still to create either the different knowing, because let's say that the keys aren't hard-coded. I can pump in different keys and pump in ciphertext. And that gives me that ciphertext to key mapping, which then when I see that ciphertext appear, I can look up what key uses it, and now I plug the key into the oracle and I'm good to go. The other thing is, obviously, if I grab everything, you can look in memory. You can see if they do a key exchange at any point. A lot of applications, unfortunately, do the key exchange in the clear or things of that nature. And so then you grab the key and you're good to go there. Or you can use the sled to just do a padding attack against it. And that's actually one of the more common usages, is you create a sled that then attacks the oracle, and there you have your padding oracle attack.